Hello, 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 hello. Okay, hello, Gianna. Hello, Jada. Hello, Brianna. Hello, hi, Montserrat. Hi, Kay. Hello, Tobias. All right. Hello, Stephen. Hello. Oh, got it. Direct chat person. Got it. Thank you. Okay. Thank you. Sounds good. Hello, Brianna. Top of the afternoon. Hello, Jasmine. Okay. Oh, there's more people. All right. We're going to get rolling fast. This is it. Here's the story. I want to say, yes, I know. For real. Yes. Thank you. Yes, any day. They keep coming like any day. I'm so sorry. Yes, direct chat. You're the one direct chat. If I'm, I actually I thought I had yours, but I guess I didn't. So like momentary, daily. I promise. I'm so sorry. I mean, any day. And yours is actually next in the queue. I thought I had already done yours. Person who's in the direct chat, and you're the only one. So yes. And people that have waited this long are actually getting certain point compensations for that too. You'll see on the exam. If you good afternoon. You can ask me more direct. You could text me, please do. If you okay. In fact, oh no, you're very kind. You're very kind. No, you're very kind. Okay, so a couple things to everybody. Since this is the last one, I can't say enough how much I'm enjoying this group, and I know I'm causing some of you some anxiety, which is the last thing I want to do because you don't deserve it. You've been a great group, and I'm really looking forward to seeing this group again next semester, electronically or dimensionally. And I mean that, but I know we've got to get through some big things before we get there. So a couple of things, so like logistical things. Wait, so everyone, hold on, where's everyone? Okay, so first of all, just in case, I'm putting in the chat right now, just most of you know this or have access to it, but just in case, I know that this is that time of year where all of a sudden we discover things. Hold on. Okay, so in the chat, I just put my phone number again I mean, many of you have used it a lot, which is great. Some of you have never used it, and maybe all of a sudden now, whatever. If you have any questions or anything, feel free to email or text. Just tell me who you are. If you never have texted before, more people coming. I'm going to sound a little, I apologize in advance. I'm going to sound a little rushed because I want to make sure to hit everything before this final class is over. My goal is to have as many of you do as possible, legitimately with that, but I want you to do well. You want to do well. We want to maximize the possibilities of that. Those of you who are still waiting on information, I can't apologize enough. And I can also say that people who just got things back or just about to are getting a few points of compensation for their trouble. Nothing major, but as an acknowledgement. And the longer things take, the more generous I have to be when I'm making close judgment calls. Any close judgment calls go in your favor, believe me. I mean, I hope to think that's always true, but certainly true in a situation like this. So here's the deal again. Your actual final exam will be posted Wednesday night, like not tomorrow night, but the next night, and it'll be due back Monday of next week. Again, it's take home, open notes, all that kind of stuff. You have a practice document already in your possession. The final exam itself will be taken from that practice document. That is to say, there'll be nothing on the final exam. There'll be no surprises, nothing that you don't already know what's coming from the practice, but some things might be shaved off, or I might give choices, or somehow I'm going to try to make your actual final thing a little bit shorter than this practice. So if you know everything on the practice, you're set. I mean, that's, the bottom line. We're going to spend most of today walking through the practice. I'm going to say whatever I can to be helpful about the practice today. Once we get rolling, that's mostly what we're going to do. Of course, any questions you have, put in the chat. And, oh, and yes, okay, I see something in the chat already. Certainly, up until tomorrow, you could still, or we can even say till Wednesday. I mean, technically, so old homeworks and things like that, or an updated or improvements, anything you're looking for points. I mean, technically the shop is supposed to close tomorrow on the last day of classes. I don't mind giving you till Wednesday, since I'm not even going to post the exam till then. You can still take till Wednesday to post and also because I'm taking so long with some of you, any old opportunities for points that you can find between now and Wednesday, sure. I mean, of course I can't guarantee how, I mean, you're just going to get the points. You're not going to get feedback on them, obviously, but sure, I will take anything you find that is an opportunity to give you more points. You can submit until Wednesday. After Wednesday, I would say no, partly for your benefit. I would say no, not after Wednesday, because then you should just be focusing on the final. And I promise you this, I do promise, it is far more worth your time, like point-wise and grade-wise. After Wednesday, don't worry about old stuff anymore. It's literally not worth it to you, to your grade, to any, it'll just confuse me too. As of Wednesday, once the final is posted, just worry about the final. Really. Again, please just know going in that I'm rooting for you as much as we're not against each other. It doesn't guarantee that everybody's getting an A, but we're both looking for you to get a high grade. So I'm also going to say, like I said before, because some of these documents are taking me so long, again, whichever exam you do better on, I will somehow weight somewhat more heavily than whichever exam you do worse on. I'm not throwing anything away, but if you do better on the final, I'll give that a little bit more weight in the calculation. If you did better on the midterm, I'll give that a little bit more weight in the calculation for each of you individually. Again, that's just a way of saying also, I'm not looking to cheat for you. I'm not looking to give gifts that aren't like merited. I'm not looking to give grades that weren't earned, but I am looking to find anything you give me, I'm looking to find the best possible version of it and the most generous interpretation of it to give you the best possible grade you can get from the best possible work that you've done. I mean, I've said it a million times, I just want to make sure that's still clear for the last week when we're all a little bit stressy about tying up loose ends. Now, today, I'm going to, oh, great. Oh, no problem. Wait. Okay. There's a lot in the direct chat. Wait, these are legitimate questions. Sorry. And I appreciate all these questions. Sorry. Oh, okay. No. All right. I see direct chat person about the laptop. Totally fine. No, that's cool. That's cool. And then direct chat. There's a lot in the direct chat. Hang on. Yeah, honestly, Wednesday night is fine. I mean, I'm saying Wednesday, like I'm saying I won't take more homework after Wednesday. If it's going to make a difference in your life, and if you really have you've already budgeted out your time, you've got Orgo and for example, things like that. Sure, Wednesday night is fine. I'm just saying Wednesday night is fine. Okay, Wednesday night is fine. I'm just saying it will be once I've already posted the final and I'm starting to get finals back, I should only be grading finals. Like I should have it worked at, right? I mean, for your sake too. So just not past Wednesday night. And really if you're trying to simultaneously focus on old homeworks and the final, it's not going to help you on your final. And the truth is the final is worth more than any one old homework. So yeah, Wednesday night's fine, but don't go past that. Okay, cool. Wait, I'm still looking at direct chat. Oh, good afternoon. Good to see you. Wait, great question in the direct chat. And yes, I have gone over it, but no, this is that day to make sure that we're clear to everybody. Yes. It says in the direct chat, you probably went over this already earlier in the semester, but the homework points go toward the overall grade, right? Like if you don't do one, you don't get points taken off. That's really important. The answer is yes, that's correct. Let me just repeat. If there's any homeworks that you didn't do, you're not getting points taken off. That is correct. It's also correct that homeworks that you did do, but you didn't get a perfect score on, they're not percentages. You're everything that I'm not yelling. I want to make clear to I understand that some of these things don't seem clear until the very last day. That's what we're here for on the last day. Right. Anything you've ever done in this class other than straight up exam, or in this class, like, and other than lab, like lab is different, but anything you've done in this class other than a straight up exam is just that many more extra points that in the end get added to your grade. It's not one for one. Like if you have, you know, 100 extra points piled up from homework and stuff like that, you don't get 100 extra points. There's a scaling factor, which I don't know until I sit down to do all the grades. But the scaling factor is the same for every single student, guaranteed. So, and it's designed to make sure that students do well. I promise you. So again, just to say this, I know a lot of you get this, but even if there's one person who's worried about this and trying to make decisions in the last week, it's important that that one person and his or her friends understand, like there's a scaling factor. Say it's like 12. Say the scaling factor turns out to be like 20 this semester. That means if you accumulated 200 extra points on homeworks and game turns and all of these things, then I divide, if you have 200 extra points, I divide it by 20. So then that would literally mean you get 10 extra points on your grade. That is correct. And the important thing about that I'm answering someone's question and saying to everybody is, like, that means if you have 200 extra points on your homework, but it was out of a possible 600 or something, that doesn't mean you're being penalized at all. And it doesn't mean you got like 33%. It just means there's someone else in the room maybe who got like 600 points. So they're getting even more extra points on their grade. That's all it means. It's like everything is like extra credit in that sense, and it all counts. It just doesn't count one for one. It counts by a multiplier that I just don't know until the end. So please, person in direct chat who just asked me that, please just confirm if that makes sense to you now. I just want to, so don't worry about, so the bottom line is, do not worry about things you haven't done or things you got wrong or anything. It's just about anything you can do or have done. Oh, cool. Okay. Just helps you, all of you. Okay. And that's also why anyway. Okay. So I think that's clear. Okay. So today, all right. So today I'm largely going to be like sort of walking through the, okay, other people are coming, walking through the final exam and talking you through it. Like I won't even be necessarily writing tons of solutions. I'm going to be walking and talking through like advice and tips of what to do on this final exam. Okay. Okay. So I'm going to walk through. You should stop and ask me questions if any instructions are unclear. Like I think you've seen most of this material before, so the exact solutions and stuff are all in your notes and videos from past classes, but I'm going to walk through the final exam. So you should like walk with me and see if, you know, if you get what I'm asking and you sort of can picture what you would do. Okay. But I'm going to also tell you right now, right. And again, that final exam will be posted in 2 days. Is that right? Yeah. Posted in 2 days, then due back on Monday of next week. And we have to be strict about that. That is a final exam. We do have to be strict about that. And then I have to like rush the grades and everything to get them in. I'm going to tell you right now that there's on the very last page of the exam, the very last page is where some slightly new questions from just slightly new equations from just the last couple of days of class come into play. And I'm not asking them at the high level, and I'm not asking them at a deep or long level. I'm just sort of asking plug and chugs about a couple of final equations that were given to you, or at least one of them was given to you last week. I'm going to tell you all right now. I'm going to make sure you're listening to that, or make sure you hear me. For a full sort of walkthrough and advice and solution and equations and procedures for exactly what to do on that last page with those newest equations, that's what I spent all this morning in the other section doing on purpose. So that video will be posted, and it'll be put into your Google Classroom as well. But for all the tips of like the newest stuff that's asked at a superficial level, but it's nonetheless new and unfamiliar, all the stuff on the last page, watch the video that comes out tonight from this morning's section. Similar with you guys, I'm going to walk through more thoroughly all the main pages of the exam. So and they'll watch. So you should both watch both videos is what I'm ultimately saying. But I'm going to just stop right now and just make sure, is it, so any of the new things about springs or work and energy, I covered this morning. There'll be a video about that. And again, it's just to get the basics so that you could sort of plug and chug in the basic equations and get those questions right on the last page. And I'm doing all that, sort of tucking that in so that, because you need that material, at least at that level, you need it for starting off Physics 204. Okay. So just watch the other class video to get all the questions perfectly right on the last page of the exam. Other than that, I'm going to walk you through the rest of it in this class for the pretty much the rest of this period right now. Can I just pause for a second? Can I just get a show of electronic hands? Do you understand what I'm saying about the two different videos, the two different classes? Thank you, Samaya. Thank you, Abdel. Thank you, Montre. Okay, cool. Thank you, Brianna. Thank you, Jose. Awesome. All right, I'm going to take that as awesome. All right, so that's clear. All right, so I'm going to start in a minute, like sort of walk. I'm going to switch the screens and walk through the final. You should definitely put questions in the chat. If I decide I can't answer them now, like if I decide it's not efficient to answer, I won't, but you should put questions in the chat. Oh, Sumaya. Oh, sorry, Sumaya. Are you just still raising your hand from a second, or do you have a question? Sorry. Or is it, or it's probably just from before? Okay. If you do have a question, just shout it out. It's fine. But okay, last thing. Again, I'd rather, believe me, I'd rather like be nice and calm on the last day, but I sort of never am. One other thing, just to really clarify about, because I know it's hard, even if you've gotten back everything, which I mean, some of you have, but it's hard to know exactly what your exact grade is in any, oh my gosh. That's a little scary, whatever that is. But I know it's hard to know your exact grade at any moment because my grading system, again, is complicated. It's designed to give you lots of different paths to a high grade. So it's designed that there's more than one way to get a high grade. So that means it's a little hard to know at any given moment exactly what your grade is. I recognize that. Certainly, again, I'll tell you right now that if you did get an exam back and you got in the 80s or something, that you're definitely in A range. I could say that much. If you're in 70s, you might be maybe in B range, but that doesn't mean you're definitely not out of the running for an A, especially depending on what you do on the final and what's going on in lab. But one thing to all of you, just so in case, this one thing you need to know, in case there's some really horrendous information that comes to me very late in the game, like when I'm already grading all the exams and I'm turning my grades in to CUNY first that are due right after Christmas or something like that, like the 27th. If I'm just telling you right now, you should know what I do. If all of a sudden I find out that one of you, like really actually, if I were to submit all the grades right at that moment, that one of you would get a D or an F, and I mean, some people know, some of you I've like talked to already about that, or you already know there's something dangerous going on. But if on one of you, I just suddenly find out, and I'm surprised to find out that, it looks like there's a D or an F about to happen, and I didn't really see it coming, and therefore it's possible you didn't see it coming, then you're not going to see a D or F just surprisingly appear on CUNY first. That's not going to happen out of nowhere. If you see an I on CUNY, I have to tell you this, if you see an incomplete on CUNY first, when the grades come out, and this does happen, if you see an I don't know if you've ever got one in another class, usually they're for medical situations, but if you see an I, it means there's something incomplete. It means that I'm missing something, and it could be me, or you are missing something, and it could be you, but I am not going to assume the worst, and I'm not going to drop a bomb on your head. So if you see an I on CUNY first, what that means is reach out and contact me, and we will make an appointment, and we'll figure out what's going on. Like whether you're missing something or I'm missing something, or the whole situation is disastrous and we need to do something to rectify it. If you see an I, it is an opportunity, it's an invitation for you to reach out to me and see what we can work out to make sure that basically you get an okay grade and that at least you pass the class. Okay, so don't panic if you see an I. And a lot of people have turned I's into perfectly reasonable grades in this situation. As long as they work with me, we work together to figure out what's going on, or if something has to be redone, or a midterm has to be totally redone or something like that. So if you get an I, don't be panicked, don't be angry, just reach out to me and say, okay, I noticed there's an I, what are the next steps? And we'll figure it out from there. Certainly, if you get an I and you never reach out to me or you don't notice it for like, it is true that I's, if they're not dealt with, I means incomplete. If you get it, or INC, if you get an INC and it's not dealt with at all for the full semester, like all semester, next semester goes by and you've never reached out to me, then it does turn into like a WU or something. It turns into something that you don't want. So but it doesn't have, as long as you reach out to me, then we'll figure it out. So that's what I do if all of a sudden there's going to be like a major negative surprise. Okay. And that's not really what I'm supposed to do. I don't think exactly, but that is what, so just know that if you see that, don't panic, just reach out to me. Okay. Wait, can I just say, did everybody hear that? Are you clear on that? Okay. I'll totally take Katya. Okay. Thank you, Katya. Okay. Thank you, Abdel. Thank you, Gianna. Okay. Okay. So that's like the worst, that's getting all the worst things out of the way. Other than that, obviously, I want everybody to have a good holiday and good grades, and I wanted to see everybody next semester. So now, for the remaining time, let me just change the view. For the remaining time, we're going to walk through this final exam, which you hopefully have in your possession. I mean, I think you do in Google Classroom. I'm going to switch this screen. Yeah. Oh, wait. One second. Wait, let me just think for 1 second. Yeah, okay. I'm making the choice here. This may be a risky choice. I am making the choice that it's better for us all to be looking at this together than for me to be writing things. Okay. So you can see this, right? Okay. All right. So again, your final exam will look extraordinarily like this, just hopefully somehow maybe be a little shorter, maybe you'll have choices somewhere, but be prepared. You should be prepared to be able to do everything on this exam. Okay. All right. So part 0 is, as it says, is the setup. It's presenting you with an inclined plane, inclined at angle theta. There's no friction yet. Oh, I'll tell you right now. And there's a small misprint there. It says, let the small height be known as, you should write, it says inclined by some small height and small angle. The height doesn't matter for a long time in the whole exam, but there should be a letter H there. I'm sorry, where it says, let the small height be known as H. Please put in the letter H. So I'm on like the right in the middle where it says, let the small angle be known as theta, let the small height be known as, it should say H. Okay, assume that objects free fall at G. Da, 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 da. Okay. So you're going to do a very similar thing in part 1 and part 2, but part 0 is the setup. I'm going to tell you right now, if you're taking notes, which I would advise, or you're taking advice, which I would advise, even before it asks you anything in part 1, even before like it starts setting up how to do things, it starts asking you questions like system schema. Let me say that you should draw your own, you should draw something very much like what's on the sheet right now. Okay. You should provide an inclined plane with an angle theta with a block that has mass M labeled on it. And you should do that. You should just provide a picture of the situation like I've done here. One of the important things about this picture, besides the fact that it's telling you what we mean by theta and what we mean by M and what we mean by G, and G really should be in my picture too, is that we're going to use the orientation of your picture for here on, and we're going to be consistent. Like my slide points to the left and down, right? On your actual exam, I'm not to be weird, but I might flip my picture and make it point to the right, or I might not even provide the picture at all. Like I'm going to, like one way or another, you have to provide a picture of this slide, and you have to be able to analyze the slide, whether it's pointing down and to the right or down and to the left. Like honestly, like we're going to do a lot of things where we break up force vectors and stuff. Don't just memorize the force vector pictures, because they're all based on whether this slide is oriented to the left or to the right. So we make a decision at the beginning, okay, this slide happens to be oriented to the left, like it's falling down into the left. That may or may not be a good choice. Whatever choice you make, you stick with for the rest of the problems. Okay, whatever. So that's the diagram. This is this mass on an inclined plane. It's not frictional. All right, so you get to part A. It's good. It says the acceleration, meaning that the ultimate goal of this whole thing, of this whole part A, your ultimate goal is to find the acceleration of this block as a function. You're not going to get a number at first. You're going to get something. In fact, I'm going to tell you right now what answer you're going to get. Ultimately, after you go through all the parts, your goal is to get that A equals G times sine of theta. Like I mentioned in class, last class, your goal is to get A equals G sine theta, but you have to, meaning that's how A depends on G and theta. But to get there, we got to do all these steps. So first you're going to draw a system schema, right? That's the thing with the dotted circles and the solid circles. I will tell you right now, I mean, we've done this a bunch of times, but I'll tell you right now, the system schema is just the objects that are interacting with your mass. Like your mass gets a dotted circle in the middle of your picture, and then you're going to draw a solid circle for every object in the world that is exerting a force on your mass, every object in the world that's interacting with your mass. That means planet Earth will get a solid circle, and anything and everything touching your mass will get a solid circle. So in this case, that's the inclined plane itself, is the slide. So you'll have a solid circle for planet Earth. You'll have a solid circle for the inclined plane. And the inclined plane in this case is not rough. It doesn't exert friction. So in this case, you can just connect the inclined plane to your dotted circle with one line. Planet Earth will get connected to your dotted circle with one line. And that's all you'll have in your system schema. The purpose of the system schema is to see how many forces are going to become arrows in your pure free body diagram. Every one line in your system schema will become an arrow in your free body diagram. In this case, because there's no friction, you'll really only need two lines in your system schema, which will become two arrows in your pure free body diagram. If you have an extra line, it's not in your system schema for this, it's not a crisis. I could understand why you might have an extra line, and that's fine. But all right, so then it says draw pure free body diagram of the mass. So now you're going to draw a dot representing the mass. You're going to draw an arrow whose tail starts at the dot and whose tip goes in the appropriate direction for every force acting on this mass. I'm going to tell you right now, there's definitely going to be an arrow pointing down. And so there's going to be one arrow for every line that you just saw in your pure free body diagram. Draw an arrow down representing planet Earth pulling on your object, representing the weight of your object due to gravity. That is labeled mg, mass of the object times like the 9.8 number. So you'll have one arrow pointing down that's labeled mg. Then you'll have another arrow that represents the plane pushing against your block, right? And if you, now here's where we have to be consistent. If you look at this slide, the slide is oriented like that. So the surface of the slide, the surface of the plane is pushing, well, it's a mirror image on the camera, right? So I always do this. Okay, so the slide is pushing up on your block perpendicular to the plane of contact, right? That's called the normal force. Normal means perpendicular to the plane of contact, the pushing between the two surfaces. So you'll have an arrow going, in this case, up and to the left. Now, again, if on the actual final exam, if I decide to be, I don't know what, if I decide to flip this slide and make it turn the other way, which I might, then your slide would be turned the other way, and then your normal force would point the other way. I hope that's clear. Like it's not a memorizer. It's like, but so the normal force points, it's a push that's perpendicular to the plane of contact. In theory, you know, because you got two surfaces pushing against each other, I've said 1,000 times in class that whenever you have two surfaces pushing on each other, they generally generate two lines in the system schema, right? One that represents normal pushing and the other that represents frictional pushing. If you have two lines in your system schema, it means you've been paying attention in class and you understand a lot of things, and that's good. And I probably won't penalize you for that or anything, but just understand that here we're talking about two smooth surfaces where the mu coefficient is 0. So there really isn't any friction happening here, and that's to make our life easier. So you don't really need that second line connecting the two circles in the system schema, and you don't really need an arrow representing friction here because there really is no friction here, we were told. So the whole free body diagram, honestly, the pure free body diagram of this case is mg down, normal, pointing up and to the left. Last point. Oh, there's something in the chat. I'm sorry. Oh, great. Oh, that's a great question. Okay, sorry. Someone in the direct chat is asking for the FBD. Does it always have to be a dot with the arrows, or can you do a box or circle with the arrows pointing where they're supposed to? That's a very fair question, because I know all over the internet, people do it differently. They don't always do a dot. Totally fair question. So as long as they actually are arrows that are pointing in the correct direction, I wouldn't take, if you draw a box or something, I don't think I'll take off points. I would advise, I do think strategically, there's a good reason that the tradition of a dot is a better tradition than a lot of what you see on the internet, or what a lot of, in my personal opinion, is that the dot is better for one main reason, well, two main reasons. One is that the dot really shows that it's not a system schema. It really shows that you know the difference between a system schema and a free body diagram. Two, the dot is meant to demonstrate to all of us that in a free body diagram, we are explicitly and consciously analyzing all of the forces that are acting on a certain point in space at a certain point in time. Like, that's really what the free body diagram is all about, is something instantaneous and localized. And the dot emphasizes that aspect of the free body diagram. So I will say that I strongly prefer the dot, but so when, you know, if you're even asking this question and you still have room in your mind to adapt or to expand, I would suggest strongly that you get in the habit of the dot. It'll serve you well in Physics 204. But right, honestly, I know that there's variation across the web, so I probably would not take off points if you okay, great, thank you. Oh, but to everybody, by the way, you know, the other and it's a really fair question because it shows someone's studying and paying attention and all that. And I know these judgment calls can be very judgmenty, but to everybody, let me also say, there's a lot of judgment calls involved here. But the thing is, it's hard to know where I'm going to be generous and flexible about and where I'm going to be strict about. So for example, like, I couldn't say it's not that big of a deal whether you do a dot or a circle. And if you really trust yourself and have been paying attention, you can make that judgment call. But for example, the arrows, it really does make a difference. In system schema, they had better not be arrows. And in the free body diagram, they had better be arrows. A lot of people did lose a lot of points on the other exam where they made triangles out of things that looked like reasonable triangles, but they weren't arrows. I'm actually super strict about that. And all I'm saying to everybody is, I know at this stage, it's still hard to know sometimes where I'm going to be strict and where I'm not. So when in doubt, do what I do. But okay, great question. I'm going to go on. And thank you for acknowledging. I totally appreciate it. Okay. All right. So that's a pure free body diagram. Okay. Now, similarly here, question 3. It's going to ask you about the Newton's third law pairs. I identified present in your pure free body diagram and or in your system schema. Now, here's the thing about this. Here's a case where I have a lot of flexibility in certain aspects, but I have no flexibility in other aspects of this question. So if you're in doubt, just do exactly what I'm doing. I'm asking for every action-reaction pair sort of suggested by the situation that we're looking at. The real thing that I'm trying to get at here is that every force itself is an action-reaction pair. Every force is a reciprocal symmetric interaction. In a way, the system schema makes this even more clear than the free body diagram. In a way, my advice for number 3 is to look back at your system schema. In the system schema, you have 2 lines. Therefore, that means you have 2 interactions. Each one is the connection between 2 objects. Therefore, you have 2 action-reaction pairs. Now, similarly, in the free body diagram, you have 2 arrows. You're going to have 2 action-reaction pairs. The main thing I'm trying to get at right away is that do not think. So what I am saying is that every arrow you see in your free body diagram is an action happening to your mass. It has a reaction that your mass is doing back to something. That's pretty clear in the system schema. Like, so for example, here's what I'm saying. The first action-reaction pair is the pair of weight of mg. The pair is, one exact way you could say it is, Earth pulls mass down, therefore mass pulls Earth up. That is an action-reaction pair. The action is the Earth pulls the mass down. That's the down arrow in your free body diagram, or that's the line connecting the mass to planet Earth. But you see, it's in the system schema. But you see, it's a line. It's just an interaction connecting the block to planet Earth. In the system schema, what we're really trying to get across is the mass doesn't have like some sort of conscious priority over planet Earth. If the mass is pulling on planet Earth, then planet Earth is pulling on the mass. End of story. Now, you don't see that in the free body diagram, because by the time you draw the free body diagram, we're so interested in directions, we're not including planet Earth in the picture anymore. And we're not including like the tabletop, the inclined plane in the picture anymore. Each successive picture we make is focusing our attention more and more on specific directions, but they all begin with objects. So what I'm really trying to say, I'm going to give you the other. So action-reaction pair number 1 here is Earth pulls mass down, therefore, or semicolon, or colon, or dash, or something. Therefore, block pulls Earth up. That is one pair. That is all implied by the down arrow in your free body diagram. The other pair is the normal force pair. The other pair is inclined plane pushes block up and to the left, like diagonally, you could say, up and to the left. So inclined plane, this is the normal force. The inclined plane pushes the block up and to the left. Therefore, the mass, the block, pushes the inclined plane down and to the right. That's the other pair. Now, I could be it's only 2 points. I should move on in a second. But what I'm really trying to say is mg and n themselves are not a pair. The gravity arrow down in some diagram is never a pair with any other arrow in the same diagram. Each arrow is its own pair. That's what I'm really trying to say. And in each pair, when you write it out, sure, there's like some flexibility. Like I'm saying blah pulls blah up. Sure, you could say like blah pulls up. Like you could say mass pulls down on Earth instead of saying mass pulls Earth down. Like, yeah, there's that much flexibility in what you do. But don't say that the mass pushes down on Earth. That would be very wrong. The mass definitely does not push the Earth away from it. Or don't say that the Earth pushes the block down. That's wrong. The Earth pulls the block to it, right? So what I'm really trying to say, the format is, in any action, you say blah pulls or pushes blah in a certain direction. And then the reaction should be the same verb. If you put pull in the action, then it's pull in the reaction. If I pull you, you pull me back. If I push you away, then you push me away back. It's never, ever that I pull you and you push me away. That is not an action-reaction. So it should be the same verb in both, and the direction should be flipped. If I pull you to the left, then you pull me to the right. That's how action reactions work. And for every arrow in your pure diagram, there should be a full pair. That's how that works. Okay. Oh, I'm looking in the chat. There's things happening in the chat. Oh, so exciting. Sorry, the block is the mass. Yes, the block is the mass. Sorry. Oh, I see. Oh, okay, cool. So you guys are good, but good conversation. And you totally, that was like multiplayer co-op. That's awesome. Yeah, the block is the mass. And I try to use the word mass just to, but yes, right. You got it. Okay, cool. All right. Oh, but as far as that's concerned, just in case I run out of time or something, say when we get to the point where later on in here, friction's involved and asks you to do like action reactions involving friction, a word of advice. I mean, all of this is, I know I'm giving you the answers now, but I'm telling you, I've done this for years. I can give you the answers now. And as someone's direct chat question, like there's a million ways to do this right, but there's also 3 million ways to do it wrong, even if you got the answers in advance. One example is, I mean, hopefully it sounds like what I'm saying makes sense, but year after year on exams, I'll get phrases like what I'm saying is once friction's involved, okay? Once friction is one of the arrows in your diagram, people will frequently say things like they'll say something like friction pushes the mass to the right. Therefore, mass pushes friction back to the left. You can't say that. Friction is the phenomenon. Friction is the name of the interaction. Friction is the force. The whole issue here of action-reaction pairs that we're trying to get across in the system schema is you can't have an interaction unless you have two objects that are interacting. So you can't push on friction. Friction is not a thing, and you can't pull friction. Friction is that the inclined plane is pushing on the block. And therefore, by Newton's third law, the block pushes back on the plane. You see what I'm saying? And you never say block mass pulls down on gravity. I mean, people say it all the time, but they're wrong. Or don't say gravity pulls down on the block. Say the earth pulls down on the block. Therefore, the block pulls up on earth. We're trying to emphasize here in a very important way that a force is not a thing. A force is the act of two things interacting with each other. And you can't believe in a force unless there's a thing there to be doing it to another thing. All right, I'm going to move on, but hopefully that's somewhat clear. Hopefully, but that's a place where people lose points all the time. Anyway, all right. So now we go to 4, where it says using the coordinate axes specified above, draw a component free body diagram of the mass, zoom in, blah, blah, blah. All right, some words of advice here. And again, I may not get to every single part of this exam, but you also, if you've looked at it or you're looking at it, you see there's a lot of repetition in this exam. So hopefully I can give you the big picture. We get to this part 4 here. First of all, note it's not a coincidence. Everything that happened before this part, the system schema, the pure free body diagram, the action-reaction pairs, all of that would be your same answer no matter what coordinate system you choose. All those answers that we just said, if you're somewhat confident of them, they're going to be your same answers when we get to part 2, or part B, whatever it is. Roman numerals 1, 2, and 3. You'll have the same answers again, and they won't be wrong. And you can state this is the same as before. But now, the whole deal is we've got these two forces in the diagram, and they're not along the same axes as each other. Like they're not parallel to each other, or they're not perpendicular to each other. So in order for us to do F net equals MA, we're going to have to break up at least one of these forces to get components that lie along an x-axis and a y-axis. F net equals MA applies independently, that simultaneously to each axis. So this is where, so now what a lot of people kind of maybe think when they're doing this is you have to decide now whether you're breaking up N or you're breaking up MG. How do we decide that? We decide that we break up whichever one is not along what we've designated as axes. How do we designate axes? We make a choice. This whole exam is trying to show you that different choices can be made and they lead to different consequences in physics. So at this part of the exam, supposedly, we've already just agreed to make the choice, I'm scrolling back, that our axes look like this, right? We're just choosing that our x-axis is lined up with the horizon or the floor of the lab room, and the y-axis is lining up with a wall. So therefore, any force that doesn't lie along one of those two axes is going to get broken up into components. So in this case, here, on page 4, Roman numeral 4, we're going to zoom in on the normal force because it, in this case, is not lying along the X or Y. So I would recommend here, literally zoom in, like I mean, if you're listening to me right now, I would highly recommend, before you even make a new free body diagram, just zoom in on that end. Like it's going off at some angle. It's an arrow that is itself the sum of two tip to tail leg arrows, right? I mean, it's a hypotenuse of a triangle. It equals the sum of some leg, like a horizontal. So like if this arrow is going up and to the left, it's the sum of some arrow that's going to the left. Then at the tip of it, start the tail of an arrow that goes up. And now you have the two vector components. One goes to the left and one goes up of this arrow. You're going to break them up. One's going to be n, so n is the hypotenuse, n standing for normal force. One of these legs is going to be the sine, one's going to be the cosine. Of what? Of theta. What do I mean by theta? I mean the original theta that was given in the problem. Like supposedly we measured this theta in the lab. We could see it. It's the angle that's made between the plane itself and the horizontal x-axis. So now be very careful here. That's the only theta we know. Like that theta is known, even though it's not a number, it's a given, that theta. When you go to draw an n vector and you divide into two components, and I'm highly recommending that you zoom in, draw a zoomed in n vector with two n components, make it a vector triangle, not just some raw geometric triangle that doesn't have tips and tails. When you hone in on this thing now, the question is, in this right triangle that you just made on purpose, like leg, hypotenuse, in that right triangle, okay, one of the angles is a right angle. It's a right triangle. The angle between the x-axis and the y-axis is obviously 90 degrees. But one of the other two angles is the theta that was given in this problem. If you really think about it, and you do have to think about it, you might even want to jot down a little quick explanation in your exam if you're really trying to show things. I think that the angle, and maybe I should draw this now, but I think that angle theta that we're looking at right here, that's given that we know, I think it's the angle at the top of your triangle. Because which is subtle and difficult, and you may want to discuss with one another or think about. But if this angle is the angle made between the plane and the horizontal, your normal force vector, your arrow going like this, is not the plane, right? It's perpendicular to the plane on purpose, by definition. It's perpendicular to the plane. So the angle it makes with the horizontal is not the same as the angle the plane makes with the horizontal. In fact, if you really think about it geometrically, or look at it, or do geometry in your mind, you realize that the angle this thing makes with the horizontal must be the complement, must be 90 degrees minus the angle that was actually given in the original plane. I'm not saying this to confuse you. I think it is a confusing point, but I'm not saying it to trick you. I'm just saying the reality is the normal force goes perpendicular to the plane by definition. Therefore, the angles in its little right triangle must be 90 degrees minus the angles in this triangle. I don't know how else to say it, but that. So the angle on top, the angle between the normal force and the vertical, is actually theta. And the angle at the bottom is actually 90 minus theta. Therefore, the horizontal component of the normal is sine. And the vertical component is n cosine. There's other ways I could explain that or show you, or there's other ways you could test that in your mind, but that's a pretty important point. And again, it's just abstract enough. I'm telling you right now, if I flip this whole triangle on the actual final exam, make it go the other way, you have to understand this point well enough to adjust your diagram to it. So don't just like memorize where the angles are or anything. Try to follow what I'm saying. Anyway, you'll have a vector triangle where this is n, and this, the vertical component of n, is n times cosine, and the horizontal component is n times sine. If you think about it, okay, so that's part. So therefore, what do you do with that? I'm still on 4 and I'm looking at the time. Okay. Therefore, in 4, Now you take those two components. The whole idea is now you've got the two jobs that the normal force is doing, the two jobs that it's doing along independent but simultaneous axes. In other words, if the track is pushing like this, that means it's pushing somewhat like this, and it's pushing somewhat like this. To some extent, the track, the plane, is supporting the weight of the mass, and to some extent, it's preventing the mass. To some extent, it's supporting the weight, and to some extent, it's pushing the mass forward, so it falls forward, right? Because the thing is angled. So you're going to take those two components and substitute. You're going to replace N in your free body diagram. You're now going to make a component free body diagram that will have now 3 arrows in it. It'll have mg down because it always did, and we didn't do anything to mess with mg. It'll have n sine pointing to the left, and it'll have n sine of theta, and it'll have n cosine of theta pointing up, right? I mean, I kind of should be drawing these, but I want to stay on the document, so I'm not. So you had two forces, but you broke one of them up into two components, sine and cosine. So now you have a total of 3 arrows, but all of your arrows are along coordinate axes. You have 1 on the x-axis and 2 on the y-axis. Okay. Now, the purpose of doing that, now I'm going to tell you again, you do the same procedure every time. You're going to do everything I just sort of said slowly. You're going to do again later in part 2 of the exam. You're going to do it in part 3 of the exam. Breaking up components, which you were sort of all practicing on the first exam with displacement and velocity components. Now you're breaking up force components. It's a big part of this exam. You do it over and over in different stages. All your answers are always going to look different. Once you're choosing different coordinate systems, you get different answers for doing this. That's like what we're trying to see in this exam. Why do you have to break up these forces into components? Because now, finally, we can use F net equals ma to solve for acceleration. When it says apply Newton's second law to each axis independently, that literally means, okay, first we're going to go to the y-axis, for example, and we're going to say, we're going to add up all the forces in the y-axis and say that that equals m times a in the y-axis. So I would literally write, so we're adding up all the forces in the y-axis according to this picture that we just made. Like, we don't know what to do without this component picture. And we couldn't get this component picture without the pure picture. And we couldn't get the pure picture without the system schema. Like, that's like how all this works. So we look at our picture and we're like, oh, there's an n cosine theta in the y-axis and it's pointing up. I think I'll call up positive. Then there's an mg pointing down. So I'll call down negative. So I'm going to say in the y-axis, n cosine theta minus mg equals ma sub y. Like, really, I guess I just technically skipped a step. My first step really is F net sub y equals ma sub y. The sum of all of the vertical forces equals the mass times the acceleration in the vertical axis. So I literally write n cosine theta minus mg equals ma sub y. What do I mean by a sub y? I mean the component of acceleration in the vertical axis. What do I mean by that? I might even, if I were you, if I get what I'm saying and I really want to show that I get what I'm saying, I might even provide a separate zoom in on the A vector. The A vector is pointing down and to the left. It's not pointing purely down. It's not pointing purely to the left. The A vector has two components, a horizontal component and a vertical component, right? So it has, and the angle with an A does point purely along the plane. So the angle between the A hypotenuse and the horizontal leg of its triangle is theta. Like, it's not as tricky as the normal force. So you literally, A has an A cosine theta component pointing this way and an A sine theta component pointing down. So literally my final, and I'm watching the clock, my final statement for the y-axis is n cosine theta minus mg equals ma sine theta. That's my y-axis statement. Okay, that is not a joke. Like, I mean, that's like not the easiest thing in the world. It's true, it's correct, but it's a little bit clunky. It's a little bit complicated. It has like two trigonometric functions, whatever. Now, what am I solving for? I'm trying to solve for A. My whole goal here is to solve for A. I would think that I'm done, and A is an expression of other things. I might think that I'm done, but the problem is A is not the only unknown in that equation. The other unknown is N. I don't know the normal force. There's no formula or memorizer for what the normal force is. The normal force does just whatever it's doing. So what do? This is why I have two axes. I can get another equation. If I have two unknowns, I'm okay as long as I have two equations. So now I go to the x-axis. In the x-axis, I say F net equals MA. I say F net x equals MA sub x in the x-axis now. I'm talking a lot here. And by the way, I also am aware, I'm still on question 5, which is apply Newton's second law to each axis independently. It's not the easiest question. It's also technically still worth 2 points. Each of them technically is worth 2 points, but this one takes a little work. Okay. So I'm going to look at the x-axis now. What's in the x-axis? Only one force. There's nothing balancing it or anything like that. That's why the thing is accelerating. I would write N. So someone may be mute. Possibly someone who may be on mute. I'm not sure who it is, but so I write N sine theta. I'm just trying to change the view here. Sorry. Sorry. Okay. Sorry, why? Okay. N sine theta equals, N sine theta equals MA times cosine theta. That's my X statement. N sine theta is the only thing going on the X-axis. And maybe I make that direction positive. A has components in both axes, so it's A cosine theta. So anyway, N sine theta equals MA cos theta. Now I'm up to, that's it. That's 5. Apply Newton's second law to each axis independently. Now I go to 6, where it says algebraically relate and solve the simultaneous equation. All right, so here's where I've got 2 equations, 2 unknowns. The unknown that I'm solving for is A. N is also unknown. I don't know N, but I don't care about N. It's just in my way. It's just annoying me. So my advice for this is pure algebra. You're going to want to practice this on your own. Maybe I'll post some hints about this, but maybe I won't. Like, what you're going to want to do, since you have 2 equations and they each have an N in them, rearrange each equation so that it's solving for N. Like, first, rewrite each equation to solve for the thing you don't care about, which is N. Like, for example, the second equation said N sine theta equals MA cosine theta, right? If you divide both sides by sine of theta, then it'll say N equals MA cosine theta over sine theta, right? And cosine theta over sine theta happens to be cotangent theta if you care. But so write that and then do the same thing. It's going to be a little harder, but do the same thing for the other equation. Like, rearrange it until you have an expression for N. Solve. This is advice. You can do whatever you want. You could use a graphing calculator, I suppose. But I'm saying, as advice, we're solving for A. So what I would suggest, I think the easiest thing to do is take each equation and rewrite it until it is stating an equation for N. Why do that? If we don't care about N, because then you can set the 2 equal to each other. If they're each equal to N, then they're each equal to N. So they're each equal to each other. So you set them equal to each other, the N's drop out, and you have a long, complicated thing where the only unknown in it is A. Now that's going to take some algebra steps. I'm going to move on in a minute. This is like not an algebra class in physics. I don't think algebra is easy. I'm not assuming all of you think algebra is easy or fun. It's going to take some algebra steps, but if you're careful and you have plenty of time to do it, you'll do it. And I'm telling you right now that the correct answer you'll get once you do the algebra, and definitely help each other, it'll be a few lines. But once you do the algebra, you'll know you'll be right if you get the answer A equals G times sine of theta. That is the correct answer. Okay. And I'm about to move on. Maybe I should check if people are still with me. I'm not doing the algebra for you right now. That's your job. but I am telling you what the answer will be. And I'm also telling you right now. Oh, and so that will take you through 6 and 7 of this, which is kind of like you've now done the hardest part. You really kind of have now done the hardest part, because that algebra will be just enough a pain in your butt that you might say to yourself, why is the algebra putting me through this? Like, this is so annoying. Like, why do I have to go through this? The reason is I want you to see that coordinate system works, but it causes a lot of effort. So what we're going to do in a moment, so then it asks you to plug in values for A. It just asks you to, once you get A equals G sine theta, and someone asked me, one of you asked me about this in class, or it suddenly occurred to one of you, like, how this all, you're just going to then plug in different values of theta and see how this makes sense. Like, the higher and higher theta is, you'll get higher and higher values for A, and the highest value you'll possibly get is 9.8 or whatever you call G, and the lowest value you'll get is 0, and it'll sort of hopefully make sense to you why this result makes sense. But it's all to get the result A equals G sine theta. If you find the algebra really annoying, then you've actually learned something, because now we're going to move. So you plug in values. I'll tell you right now, like, the answer to A is 0. The answer to B is 9.8 divided by 2, like 4.9 meters per second squared. Or you can use 10 as gravity. That's fine too. So 10 divided by 2 is 5. The answer, if you're using 10, the answer to C is approximately 7.07 meters per second squared. And the answer to D is approximately 8.66 meters per second squared. And the answer to E is 10 meters per second squared. Yeah, I'm saying that fast because you could plug that into a calculator and you'll see. But now we go to the next page. It seems like there's a lot more in this exam, I know, but here's the deal with the next page. The next page, we're now taking the same situation and we're just tilting the coordinate system. We're tilting the coordinate system. We're just tilting the perspective at the way from which we look at the exact same facts. So many of the answers are going to be the same. Like 1, exactly the system schema, exactly the same as it was before. Don't just say that. I mean, either draw it again or tell me why it's the same, but it's the same. It's the same fact. It's the same objects. Number 2, exactly the same as before. Same pure free body diagram. Number 3, the action-reaction pairs, exactly the same as before. Number 4, now, when you draw the component free body diagram, this is where, now that we're tilting our head, and lining the x-axis up along the plane. That seems like an unnatural or weird or unnecessary thing to do, maybe. And what it means, though, is if the x-axis is along the plane, that means the normal force is perfectly along the y-axis. So the normal force now does not get zoomed in. We don't break it up. Now it's gravity that is messed up. Gravity is not along an axis anymore. So we now have to zoom in on gravity and take a little effort or a little time to show that when you zoom in on gravity and you really make a big, nice, clean triangle where gravity is now the hypotenuse, and it has 2 legs, one that points along the plane, like parallel to the acceleration, and one that points into the plane, parallel to the normal force, like arrow, tail to tip, plus tail to tip together, down and to the left, plus down and to the right, makes down. So you're going to have this big right triangle where the hypotenuse is actually a vertical line. The hypotenuse is actually mg, and mg is doing 2 jobs now. It's pushing along the plane and it's pushing into the plane. Those 2 legs that look like diagonal lines are actually the legs. They're the components. If you are careful about where theta is in this diagram, you'll again see that theta had better be between the plane and the vertical. I mean, it better be between. What am I trying to say? Like, the angle can't be between the plane and the vertical line, because theta, the original given, was the angle between the plane and the horizontal line. So it must be the angle down here at the bottom of your triangle. I'm saying that fast. You'll have to think about it, but it's the same kind of argument I made before for the normal force. You have to figure out which of those 2 angles in your big triangle actually is the original theta. But once you figure out which one it is, whatever's across from it, opposite from it, is mg sine theta, and whichever's adjacent to it is mg cos theta. So if you do this all properly, you'll find out that the leg pointing parallel to the plane, the component is mg sine, and the component that's pulling the mass into the plane, balancing the normal force, is mg cosine theta. And all of that will seem a little tricky, maybe. It seems a little weird, like what, that you're dividing up mg and you're dividing into these weird legs. But that's what you do for your component diagram. In this case, you don't break up normal, you break up mg. So your component diagram in this case, and I'm watching the clock, is you got one arrow for n, and you've got one arrow for mg sine theta and one arrow for mg cosine theta. And now when you go to apply Newton's second law to each axis independently, now this will be different from before. Now you will see why this is advantageous. Because, and if you want to jot, well, now you'll see why it's advantageous. Because now you'll go first to the y-axis. In the y-axis, you have normal minus mg cosine theta equals ma sub y, right? Normal minus mg cosine theta equals ma sub y. But what is ma sub y in this coordinate system? It's 0 on purpose. Like, we lined up our x-axis with the direction that the block actually accelerates in. The block doesn't accelerate at all along this y-axis. Like, the block is going somewhat to the left and somewhat down. So in our old coordinate system, it had components of acceleration along both axes. That made our math very complicated. Here, the block only accelerates along the x-axis because we chose the x-axis on purpose to line up with the acceleration. So here, a sub y is 0. So you could just literally, so n minus mg cosine theta equals 0. So n equals mg cosine theta. And on the x-axis, we just have mg sine theta equals ma sub x. What is a sub x? It's a. It's the full a. There's no sine, there's no cosine. It's fully accelerating along that axis. So mg sine theta equals ma. The m's cancel and you have g sine theta equals a. What I'm saying is, and I know this is a lot. Again, like, we did this thoroughly in class, like all of the past videos for the last couple of weeks, hopefully make this all clear. I'm just trying to, one last ditch effort to try to give you the big picture for your exam. I'm saying that the diagram is more funky this time, tilting our head is more funky, but now the math is so much easier, and that's the purpose. We're trying to show here the difference between, we're trying to show what physics thinking is as opposed to math thinking. We try to think about things in a physics way, so to make less math, not more. So anyway, so you write down mg sine theta equals ma, you cancel out the m's, you get the a equals g sine theta. It's the same answer as you got above. Okay, so in 7, you should get the same answer as we got above. Then asks you to plug in numbers and solve for the normal force. You'll notice this, I'm not going to say the answers now because I'm starting to run out of time, but if you just plug in, if you assume the mass is 1 kilogram and you start plugging in values for the normal force at the various angles, if you've done it correctly, you'll find that the normal force gets smaller and smaller as the angle gets bigger and bigger. Like, if the angle were 0, the normal force is fully supporting the weight of the object. But as the plane starts tilting more and more steeply, the track is supporting less and less of the object until where it's fully vertical, the track isn't supporting the object at all. So, plus, put another way, as angles get bigger in the first quadrant, cosines get smaller. So your answer for 0 should be mg. In other words, 1 times 9.8 or 1 times 10. And your answer for when theta equals 90 degrees should be 0. And the number should be getting smaller and smaller progressively in between. All right, so that's that. Now, C and D, I'm asking you to explain what I just explained. Like, hopefully you get, I'm saying Galileo's principle of relativity, absolutely, provided if you follow Galileo's principle of relativity, if you believe that the laws of physics apply the same in any coordinate system, then by choosing a different coordinate system and assuming the laws are still the same, we saved ourselves a lot of algebra. Again, part of the hardest problem of this whole test, in a way, is the algebra that you have to do to get g sine theta when you're in this coordinate system. A big purpose of all this is showing you why we're never going to be in that coordinate system again. We always tilt our coordinate systems to line up with accelerations for exactly that purpose. That's what you want to say in your words, something like that to D. Then in E, I'll tell you right now, very quickly, and I know we have 5 minutes, but we're actually almost there. We are almost there. in E, you got the acceleration. The whole thing is assuming we're starting from rest, the V naught equals 0. I'm going to tell you right now an equation that you knew at the beginning of the semester that we just got from algebra that you're welcome to use here. Remember, like, notice here, it's telling you things about, it's asking you things about velocity, and you know things about acceleration and distance and stuff, but you don't know anything about time, and it's not asking you anything about time here. The equation to use for that, when you don't know time and you're not solving for time, is A, so please write this down, I can't, is A equals V squared minus V naught squared all over 2x, where x is displacement. A equals V squared minus V naught squared all over 2x, where x is displacement. Okay. That's an equation for early in the year. And I'm not saying you have to memorize it. Like I didn't put an equation sheet in this document. Ideally, I will remember to give you an equation sheet on your final document. Plus it's open book anyway. So it's not, the point is not that you have to memorize that, but the point is that that's the suggestion of what equation to use here is A equals V squared minus V naught squared over 2x. But one other quick note to the wise is x means the actual displacement, the actual path that you travel from initial position to final position. That's not given in this problem. What's given is h, the height. So just note that in that triangle, that in the right triangle that is formed by this inclined plane, h is like the vertical leg of that triangle. X is the hypotenuse. So what's the relationship between the two? H equals x times sine of theta. Just make a note of that somewhere, maybe. I mean, h itself equals x times sine of theta equals the hypotenuse. And that's confusing because h stands for height, not hypotenuse. But lowercase h equals x times sine of theta. And therefore, x equals h over sine of theta. I'm just letting you know that as a hint for doing part E. Okay, now, I know we're just about out of time, but here's the deal. Part 4, like the last couple of pages, is what I fully explain in the other class video that will be posted tonight. So watch the other video to watch for the last pages of this exam for page like 8 and 9. But for parts 7 and 8 is all the same stuff again, but we're now throwing friction in. We're adding friction in. This is the stuff we were doing in class the last few days of Zoom lecture last week. All the same procedures, all the same questions, system schema, pure free body diagram component. It doesn't matter what coordinate axes you use, we're throwing friction in now into the diagram. It means we're throwing an extra line into the system schema. It means in the pure free body diagram, if the object is going up now, friction's pointing down and to the left. When we get to the point where the object is moving down, then friction's pointing up and to the right. That's true no matter what. For the components, you can use whatever axes you want. But here's, with 1 minute left, part of the big advice of this whole thing to see who's been paying attention, who's watching what's going on, and who's watching me right now. You can use whatever coordinate axes you want, but if you were following the conclusions of the last two parts, the second coordinate axis is a lot easier to use. Tilting your head and breaking apart MG makes for a lot less algebra. So my strong recommendation is do that. When you go to the component diagram, break up MG into MG sine and MG cosine. In other words, include all of your same answers that you had in all the prior parts of this exam. Just add an arrow for friction to the x-axis. When you're going down, make friction point up. When you're going up, make friction point down. And remember that friction, once you start plugging in the numbers to get to the end, once you're plugging in numbers to get answers, remember that friction equals mu times the normal. How do you get the normal? You'll look at the y-axis. So you'll just go step by step. It's all in the class notes from the last week. It's all in the videos. But if you get the procedure for parts 1 and part 2, it's the same procedure here, just adding in friction. You're ultimately trying to compare the acceleration up to the acceleration down. You'll know you've done it right if your time coming down and your acceleration coming down are smaller than your time. Sorry, your acceleration going down should be smaller than your acceleration going up. Therefore, your time going down should be bigger than your time going up. Okay, it's 4:20. Please text or email me if you have any questions. I hope this helped somewhat. I might post more. Again, for this last page, page 9, watch the other video. And page 9, I know I'm whatever. Okay, so you guys have been a great class. I can't wait to see you next semester. I'll hang out for a second if there's any questions, but please have a terrific exam period and terrific holidays. Goodbye. Thank you very much. Stop the recording. Thank you guys very much. Yes, enjoy. You too. Thank you. I'm gonna stop.